Good evening, everybody, and a warm welcome to the ICI Berlin. It's a great pleasure to welcome you to our third talk in the series on complementarity this year. And I should turn this off, I just realized. And those of you who have followed our program, and in particular also our research program, will know that our core project on tension, Spannung, which is dedicated to reflecting on the possibility of productive exchanges between different knowledges, systems, and cultures. And we'll also know that within this larger project, we focused last year on multi-stable figures, on so-called Kippbilder, and have moved this year to the topic of complementarity. And I'm really very glad that Harald Atmanspacher has agreed to participate in our lecture series, and very warm welcome to you here. To this series, which seeks to explore how the deceptively simple notion of complementarity can be understood and diffracted by different discourses, so as to get a sense through the series, through this collection of different talks from different perspectives, how it may help, how this notion of complementarity may perhaps help in developing inter- or transdisciplinary practices of critical cultural inquiry. And I'm very glad that Professor Atmanspacher has agreed to come for several reasons. One is that I don't need now to gesture towards an understanding of complementarity in quantum physics, which I usually do at this point, in order to emphasize that the notion of complementarity in which we are interested here cannot be reduced to the idea of different parts fitting together or coming together to fit perfectly in a kind of harmonious whole, that it's like there's a twist to it that's more complicated. And I also don't need to explain how the topic of multi-stable figures, of the Kippbilder, and complementarity may be related, because as we see already here, both aspects, I think, will be very much at issue in the talk we'll hear tonight. I'm also very glad because I find Atmanspacher work really exemplary for the kind of operation I envisage for our research project at the ICI. And we just talked about how we unfortunately don't really have many scientists here, but so we have to import them. But, and I'm no doubt biased due to my own background in theoretical physics, but I find it really extremely fascinating and stimulating the way Atmanspacher, often in collaboration with others, seeks to think through possibilities and ways of connecting theories of physics with broader questions and phenomena that are not properly in the domain of physics. There is, of course, a long tradition of seeking to relate the notorious persisting mysteries of quantum physics with any other big open mystery, such as the problem of consciousness or the relation of mind and matter, or also quantum gravity, of course. And while there's good reason to be skeptical about quick transfers between scientific models and large philosophical questions, regardless of whether these transfers are performed by philosophers or by scientists, but while there are good reasons to be skeptical, I think that to try thinking through such transfers and making them precise can be also really enormously productive. And this is in many ways, of course, a very difficult task, also because it faces the dual temptation of making premature short circuits between different disciplines, either that, or on the other hand, of presupposing a fixed radical boundaries such that nothing can be learned from the other disciplines and discourses. So the productive potential in negotiating these perhaps necessary temptations also lies probably not in arriving at an ultimate solution, but rather in blurring boundaries and creating overlapping regions that can open up possibilities on either side, even if perhaps these overlaps are most likely mismatched, and each side may also experience the operation of the other side as a kind of imperialist intrusion. So in other words, I think the point of carefully thinking through analogies may ultimately be to identify the point at which they also fail, where a limit gets redrawn in a different ways and gives contours to the bordering domains. So in this vein, I found it, for instance, very stimulating and illuminating how Atmanspacher, in an article written, for instance, with Peter beim Graben, seeks to extend the philosophical significance of the idea of complementarity by discussing a specific way in which the quantum notion of complementarity can be identified also outside of quantum physics in classical systems, for instance, when its epistemic description is considered. This particular paper I'm referring to is a rather technical paper that concentrates on systems within a mathematically well-defined framework, and at the same time indicates how its reformulation of complementarity may help to think about complementarity beyond the domain of quantum physics. And I expect that today's talk will be largely based on such analyses without probably going into the more technical mathematical details. So let me just say a few words about Harald Atmanspacher. He's studied in physics in Göttingen, Zurich, and Munich, and received his habilitation in theoretical physics from the University of Potsdam in 1995. He's now the head of the Department of Theory and Data Analysis of the Institute for Frontier Areas of Psychology and Mental Health in Freiburg, where I find it actually quite interesting that the German name Grenzgebiete der Psychologie und Psychohygiene evokes maybe a more, the Grenzgebiete evokes maybe a more problematic, unstable border regions than the idea of frontier, but I don't know which way it's leaning more towards. Atmanspacher is also a faculty member of the C.G. Jung Institute in Zurich and of the Parmenides Foundation in Capo-Livieri, Italy, as well as associate fellow at the Collegium Helveticum at the ETH Zurich and the University of Zurich. He has been involved in a number of interdisciplinary journals, including Open Systems and Information Dynamics, Biosystems, Open Cybernetics, and Systemics Journal. And since 2003, he is editor-in-chief of the journal Mind and Matter. And I think these journal titles also give you an idea of some of his ideas of interest and some of the main fields of his interests and work. Recent publications include the book Recasting Reality, Wolfgang Pauli's Philosophical Ideas of and Contemporary Science, co-edited with Hans Primas, which contains the article that I just referred to, and among many others, of course. Furthermore, he wrote the Stanford Encyclopedia of Philosophy entry, Quantum Approaches to Consciousness, and the Scolopedia entry on Contextual Emergence. Now, before handing over to Harald Atmanspacher, I would just like to announce that we have at least 2 more talks scheduled thus far in our series on complementarity. Renata Selectional will speak on events between violence and identification on May 8th. And on June 7th, Astrid Mankowski will speak on diffracting the rays of knowledge, figural and agential realism in Donna Haraway and Karen Barat. And there we will also come back to physics, but from a more media philosophy side, I guess. And also, as another further announcement, as always tonight, after the talk and the discussion here, we'll have the opportunity to go upstairs to continue our conversations and discussions with some refreshments to which you are all invited. So now I'm really looking very much forward to hear tonight's talk entitled, well, you see it, Complementarity and Bistable Perception, and please join me all in welcoming Harald Atmanspacher. Thank you.
Thank you. Thank you very much for your friendly introduction and also for the invitation to speak to all of you. I'm very glad to be here. I've seen the Institute a little bit, and I'm a little bit envious because you are really working in a very nice environment here. The scope of the talk tonight will be quite large, actually. It's not only between quantum physics and classical physics, as you indicated. This one is really between physics as a whole, and that also, of course, includes quantum physics on one side and psychology and epistemology on the other side. And so this talk will also, I think this is also the intention by the organizers, it will also set a kind of frame or a platform, if you want, for the discussions that some of us will have tomorrow. Okay, so complementarity, does it still work? Yes. Complementarity and bistable perception, that title indicates that we are really moving within the tension between physics and psychology already. Complementarity being a term which is, I think, best known from quantum physics, but I will tonight give you an idea that Niels Bohr, who introduced complementarity into quantum physics, did not introduce it out of the blue. He took it over from psychology, actually. That's historic. There's a very interesting historical story which I will elucidate to some extent at the beginning of the talk. And then, of course, I have to say something about the way in which quantum physics, quantum physicists, and also mathematical physicists use the notion of complementarity. And then at the end, I will turn back into psychology and show you how a well-developed and even formally rigorous notion of complementarity can, in recent work, be used to study certain phenomena in psychology. And among these phenomena, again, bistable perception features quite prominently. Okay, so this is the program, Psychological Roots. Then I will talk a little bit about Niels Bohr himself, His Majesty, one of the real founding fathers of the modern theory of the atom. Then I make some steps further, complementarity the modern way. How do we conceive complementarity in present days and in present science? That goes a little bit further than Niels Bohr used it. And at the end, current applications in psychology, as I said. Now, and this is another way, this view graph shows you another way of really opening up the tension between different uses or usages of the term complementarity. And I will show you some quotations here, actually two quotations. The first one by John Archibald Wheeler, himself he was a student of Niels Bohr, and he wrote in The American Scientist, 1956, complementarity, the concept of complementarity, represents in one sense the most revolutionary conception of our day. He didn't say in quantum physics. He said this intentionally, quite generally. And this is a very positive statement, of course. But then, several years later, you see Mario Bunge, Canadian philosopher of science, in his book Philosophy of Physics. He says complementarity has now exhausted whatever potency it may have had. It has become an excuse for obscurity and inconsistency. So here you see the two poles, if you want, between which many other usages of complementarity are located, if you wish. So the first one really makes a serious statement in favor of the actual value of complementarity. And the second one, Mario Bunge, is not so enthusiastic, as you can see. He notices, obviously, that many publications which use the notion of complementarity just use it in a very vague sense without any specification. And just want to, this is this notion of indifferent harmony or something. It's not enough to say that my wife is so nicely complementary to me. This doesn't tell you anything, right? And I want to address this tension from a point of view which you can find in many places, but interestingly also formulated by Franz Kafka in the process, der Prozess. And Kafka said something which itself can be called a complementarity statement in some sense. He says, understanding something properly and misunderstanding it do not completely exclude one another. And this you can easily apply to the two statements which you see on top of the view graph. So I will try to go this walk on the ridge between Bunge and Wheeler and try to convince you that complementarity is a useful notion, but you have to use it with care. Okay. Now this, I said at the beginning that complementarity actually has its roots in psychology. And this is probably the first time the notion of complementarity has been used in the literature. And that is from the Principles of Psychology, Volume 1 by William James, And James here says it must be admitted that in certain persons, the total possible consciousness, the totality of conscious activity, so to speak, may be split into parts which coexist but mutually ignore each other and share the objects of knowledge between them. More remarkably still, they are complementary. He doesn't say what he means, of course, but he just says it this way. Give an object to one of the consciousnesses, and by that fact, you remove it from the other. What the upper self knows, the under self is ignorant of, and vice versa. So in this notion of complementarity, you see already something which also will be a key point in quantum physics. You see that complementarity has to do with the notion, with the distinction between wholes and parts. The total possible consciousness would be something like the whole in this picture, and then he says split into parts which coexist but mutually ignore each other. But we have to make this much more specific to make it workable. So this was one of the, I think, at least as far as I know, this is the first time, this was 1890, when complementarity really was used in a, let's say, sort of scientific context. And the next time it was used in a scientific context, this already happened in Copenhagen, where Niels Bohr also lived. And you see this figure here, this is on all your announcement sheets. So I reproduced it here too. This figure is known as the Rubin vase, or also known as the Rubin face, or the figure ground vase, or the face and the vase, and there are many notions for it. This is a typical kip build, or ambiguous figure. And interestingly, Edgar Rubin, a Danish psychologist who studied these figures, these pictures, to a large extent, did not call the two different appearances of the stimulus, of the figure, complementary. He called them reciprocal. He was talking about reciprocal patterns. We will see that this also is important for the point in history when Niels Bohr took this whole idea up. So he studied reciprocal patterns in the 1910s, and in 1915 he published a 2-volume book. I cannot pronounce this Danish here, but in English it's visual figures simply. Is anybody here who can pronounce the Danish? No Danish people here. So that was Edgar Rubin, and Rubin was, of course, as a psychologist, very familiar with William James's work. That was very clear because William James was a key figure of very, very strong influence in psychology in those days. Now, let me say a little bit about Niels Bohr and also about the pieces of evidence which tell us today that Bohr knew William James very well and also knew Edgar Rubin very well. First of all, he also was very familiar not only with James and Rubin, but with a Danish philosopher who was teaching at the University of Copenhagen at the time, and that was Harald Høffding. And Høffding was a Kierkegaard expert, but he also was, of course, as many philosophers are, very familiar with the history of philosophy. And there are many ideas in Kierkegaard's philosophy already at the beginning, in the first half of the 19th century, which share a lot with some usages of the notion of complementarity. I have some quotations here. Qualitative dialectics. What they meant with this term is a kind of dialectics which is not like Hegel's, where thesis and antithesis always give rise to something which Hegel called a synthesis. Actually, Fichte did that before Hegel. But here, in Kierkegaard's qualitative dialectics, there are only thesis and antithesis, and their contrast remains. There is no resolution in Kierkegaard. There's this famous book by Kierkegaard in German. It's Entweder oder, either or. So this is either or. That's it. There is no solution of it in Kierkegaard's view. in this qualitative dialectics. So Bohr, there's a quotation in Abraham Pace's Bohr biography where Bohr says, I had very much to do with Hofding, and he was really very interested in complementarity. So they were talking already in the 1910s about complementarity from philosophical points of view. And here you see that they also talked about it from a psychological point of view. There's a paper by Ernst Plaum, he's a German historian of science, in which he really reports a lot of his research about how Bohr and Edgar Rubin knew each other. So the familiarity of Bohr with Edgar Rubin is very obvious in Rubin's book of 1915, where Rubin reports that he even made experiments on ambiguous figures together with Bohr. So there's the quotation, jointly with Dr. Bohr, who was kind enough to support me, I made the following experiments, and then he describes the experiments. And the last piece of evidence that I have here is the familiarity with William James. And this you can find in Gerald Holton's excellent article about the roots of complementarity, published in 1970. And in this article, he also refers to an interview which one of his collaborators, Holton's collaborators, had done with Niels Bohr himself, 1962. And in this interview, Bohr says, James is really magnificent in the way he clarifies things. If one has objects in front of oneself, they are connected to one another such that if one wants to separate them, this has nothing to do anymore with the actual situation. I think we really will have to enter these matters. Rubin advised me to read him, James, and I realized this was outstandingly wonderful. So again, this whole connection, Höfting, Rubin, Bohr, and this all happened in the 1910s. When Bohr introduced complementarity finally into physics, that was only 1927. So there was really a long time in which they were talking and reflecting and discussing these issues. Now, why did Bohr finally, in 1927, let me say, import? Because it's very clear that he took it from somewhere else, namely from psychology. Why did he import this notion of complementarity into physics? He did that because at the time, there was one of the key problems in the conceptual understanding of quantum mechanics, as this theory was called at that time, was the so-called wave-particle duality. What is the wave-particle duality? Very briefly, quantum systems can appear with wave-like properties, such as frequencies or interference patterns or something like that. Or they can appear with particle-like properties, like locations or momenta or velocities, something like that, depending on the experimental circumstance. So it can be, in some sense, the same system that sometimes, in certain experiments, gives rise to interference patterns. And in other experiments, the same system gives rise to something which looks like a moving particle, for instance. What's going on here? And I will in a minute I will tell you why Bohr thought that the idea of complementarity can resolve this kind of mystery. And what he did was this is really in the history of physics a very famous date, the 16th September 1927. He specifies this duality, which was the general notion that everybody used, as complementarity. And even in some brief period, not in 27, but in 29, he went back to Rubin's original notion of reciprocity. I told you that before. He wanted to replace complementarity with reciprocity, but then only a few months later, he returned to complementarity and stayed there. So this also gives you a little bit of a flavor how things were, when people were talking about these things, everything was in flow at the time. It was really a very vivid period of discussion and trying out concepts and rejecting them and coming up with something else and so on. Now, the idea that waves and particles are in some sense dual actually arises from a picture that is not the quantum mechanical picture of reality, but the classical picture of reality. In classical physics, that was the kind of physics that was done up to the end of the 19th, beginning of the 20th century. In classical physics, both waves and particles were mutually incompatible entities. Really, they were understood as entities in a sense of elements of reality, ontologically. Thus, in classical thinking, if one of the two descriptions is correct, the other one must be incorrect. That was the simple picturing in classical physics. And that's the reason why this kind of wave-particle duality in quantum mechanics was considered so much of a riddle, because in classical thinking, something like a system that sometimes appears this way and sometimes that way was simply impossible. In classical thinking, there is a clear either-or and nothing else. Now, in quantum mechanics or in quantum theory, the picture is different. And it's different because the wave-like aspects and the particle-like aspects are no longer considered ontologically. They are no longer entities, but they are appearances or manifestations. They are manifestations of a system under particular contexts. So, wave-like behavior or wave-like manifestations and particle-like manifestations can be mutually incompatible, but only together. They describe the system completely, in its totality, so to speak. Again, we have this difference here between the system as a whole, in some sense, in its totality, and on the other hand, in some sense, you can relate the different manifestations as parts of the picture. So there's again a whole and parts relationship here. So that was the key point where Niels Bohr came up with a kind of application of a psychological and philosophical notion of complementarity in application to physics, right? And I have another slide here which gives you some more pieces of evidence. I don't go through all these. That Bohr, as long as he lived, was always very much interested in psychological and philosophical applications and perspectives and aspects of this notion of complementarity. You can go through these by yourself, or we can come back to that maybe in the discussion session. Yeah, this is maybe the first one I can, that was already relatively early, 1931, in his Faraday lecture, where he makes a comment here. Indeed, we meet here with an illustration of the old truth that our power of analyzing a harmony, again, a whole, and the width of its perception, so that's the manifestations or the appearances, will always exhibit a mutually exclusive complementary relationship. So this is the historical, I went through this in a little bit detail because it's important to understand where the historical ideas, or how the historical ideas were, due to which complementarity became a topic in quantum mechanics, quantum theory. And in the next view graph, in the next section of this talk, I will move to a more modern understanding. And of course, at Niels Bohr's time, this modern understanding was not yet available because the mathematical formalism was not developed enough, and so on and so on. And of course, also there's progress over the years. So this is what I said already. Wave-particle duality is the historical root of complementarity, but from a modern perspective, it is understood differently. We don't talk about waves and particles as complementary aspects anymore in physics. There are different aspects, and we can understand these differences without referring back to complementarity. However, there are actually two basic formal features with which complementarity is nowadays circumscribed or specified, or characterized, I should say. And the first time when these two features really were succinctly formulated. That was done by Paul Bernet in 1948 in the journal Dialectica. I think that was a Festschrift for Niels Bohr, actually. And the first one of these two formal features is algebraic. And in this algebraic formalization of complementarity, we talk about complementary observables. And these complementary observables are complementary whenever the observables are members of a set of an algebra which is non-commutative. I will tell you what that means in a minute. I'll just give you the brief summary here. And this is, of course, the narrow scope. The narrow scope means that this is something which you can, of course, you can only apply this definition or this kind of characterization if you have, for the system that you are studying, a well-defined set of observables. And in philosophy, you don't usually have this. And even in psychology, you often don't have this. Observables are, I should say what that means, when a system is characterized by a state in which it is, then the state is specified by values of certain properties, like momentum or location or energy or something like that. And these properties are the observables. But now point two, and that's maybe the more interesting one if you are interested in the wider scope of complementarity. There you don't have complementary observables, as in the narrow scope. In the wider scope, you have complementary propositions. And this brings us into the domain of logic. What I mean is propositional logic here. And the technical term for complementary propositions is that you have lattices. In some sense, this is also kind of, it's also a set of propositions which are arranged in a certain way, that they satisfy the conditions for a lattice. I will also tell you what that means in more detail in a minute. Then you have a non-Boolean lattice of propositions. So propositions are, of course, much more general than observables because propositions you can make, a proposition is simply a statement. And of course, you can make statements about many systems without measuring anything. Observables only make sense when you can measure something. But statements, you can say this man is a just man, or this is a good man, or this is this and that is true, or it's false, or something like that. Nothing which you ever measure. It's just a statement that you can investigate from the point of view of, propositional logic. As I will show you in the following, that both of these basic formal features are not restricted to quantum theory. You can use them, of course, with the qualification of narrower and wider scope in many other sciences up to philosophical discussions and so on. And that's the real, and I have to say that actually Niels Bohr was always honest enough to state, he invented or he imported complementarity to solve a quantum mechanical enigma. But he always insisted that he was completely convinced that complementarity is a concept that unfolds its full power when you start applying it to things, to situations, to let's say to situations outside physics, beyond physics. Now the next two view graphs contain a little bit more information about what this non-commutativity here means and what this non-Booleanness here means. And maybe I should not really apologize, but make a remark here. When you invite a physicist to give a talk, then you really have to expect at least one or two equations. And the next two slides will have these equations on them. So, and I promise when these two slides are over, then the equations are gone. So this is what non-commutativity means. You all know from elementary calculation in school that if you add up 1 plus 2, the result is the same as when you add up 2 plus 1. So 1 plus 2 is 2 plus 1, or 1 times 2 is 2 times 1. That's the law of commutativity. That's called commutativity. In quantum mechanics and in complementarity, this law is violated. It doesn't hold. And you see this here. If you have two observables acting on a state is this psi here, two observables are A and B, like position and momentum, for instance. And acting on a state means, in some sense, that you measure these two observables. Now what happens is, here you apply B first to psi and then A, and here you apply A first to psi and then B. And the violation of the law of commutativity means that these results will not be the same. This is the simplest example one can think of how this can be understood mathematically. You have two, let's say we have A, something like this. This is what we call a matrix. It's a very simple matrix. You will see that again at the end of the talk. That's another matrix which is also very simple. It's only about ones and zeros. Very, very simple. And when you do the test with these two matrices, you see AB minus BA. This is AB. This is when you do the product like this, B and A, and here is the product, the other product, BA. That's this one here. And when you subtract those from one another, then this is the result. Okay? And you see, this result is, of course, everything else than zero. It's another matrix which has zeros and twos. But only if it were zero, AB would be equal to BA. So this is a very easy and very straightforward demonstration how commutativity can be violated. And this is something the experts will know, that these are the Pauli spin matrices, and this is one of the very simplest examples for non-commutative measurements in quantum mechanics. Now, why does that happen in quantum mechanics? It's not a miracle. This can be really understood, I think, in very easy terms. And the key point is that a measurement in quantum mechanics is not only a registration of a value of a system, like in classical physics. You simply assume when you measure something, in some sense you extract the value of some observable out of the system, and nothing else happens. In quantum mechanics, it's different. There's also a registration of a value, of course, but also the measurement changes the state which you have measured. And this explains in some, I think in a very straightforward sense, why measuring B first and then A can lead to a different result than measuring A first and then B. Because there's always a back reaction onto the state of the system, and that back reaction is different depending on what you have measured. So when you measure A first, then the state is changed. Then you measure B on another state. When you measure B first, the state is changed, and then you measure A on another state. And these states that remain after the measurement, are of course not identical. So that explains why this thing here does not commute. And a more general statement even here, when you change the sequence of measurements or measurement operations A and B, this change of the sequence makes a difference for the measured result. I think that this is very easy to understand. And the key difference is really that in classical physics, the assumption is that you simply, when you measure, you register a value and nothing else happens. And here really the state is changed. Also, the state is, of course, prepared in some way by the measurement. This is an additional complication. So that's the non-commutativity. And I have to do the same exercise now with the non-Boolean case here, non-Boolean propositions. Again, let me call them A and B. And both of these propositions have complements, A prime and B prime. Now here we have again a law which we usually know from school, from elementary calculations in school. It's the law of distributivity which is violated here. What's the law of distributivity? When you have let's say you have 2 times, and then square opens, 3 plus 4, bracket closes. 2 times 3 plus 4. Then the law of distributivity tells you that 2 times 3 plus 4 is 2 times 3 plus 2 times 4. Everybody knows this, right? That's not a miracle. And this fails here. Again, so this also tells, in some sense, this also tells you that our elementary styles of calculation are a very special case, actually. This is the general case. So what we do in our what our teachers tell us in elementary mathematics and elementary calculation, this is really something very special. So what we have here. This is of course not with multiplication and addition, but it's the set theoretical multiplication, the set theoretical addition in some sense. This is the intersection, and that's the union symbol. So what we have here, we have the union of B and B prime, and intersect this with A. And non-distributivity means that this expression here is different from the separated expressions A intersected with B, and the union of this with A intersected with B prime. And why is this so? Again, this is very easy to see. In an example, let's say A is something like the spin in x direction is up, and B, the proposition B, is something like the spin in z direction is up, then the complement would be spin in the z direction is down. And now we can simply analyze these terms here. Let's first start with this one. And we see B, the union of B and B prime, that's the union of B and its complement, that's always 1. And the intersection of 1 with A is, of course, A. And here, the second line, that's the right-hand side above here. Here we have the union of A intersected with B. That's, of course, 0 because they are incompatible. It's spin x and spin z. And this is the union with A and B prime. And, of course, since these are incompatible as well because B prime is simply the complement of B. So this is also 0. So we have the union of 0 with 0. That gives us 0, and that means the right-hand side is A, left-hand side is 0, A is unequal 0, so we really have violated, again in this very simple example, pedestrian example, we have violated the law of distributivity. And now again, what does it mean? Oh no, I have another example, set of examples which are maybe a little bit more intuitive, and the first one again goes back to William James. Now, this is volume 2 of the Principles of Psychology. And there he says, the true opposites, he says opposites, no comment. The true opposites of belief, psychologically considered, are doubt and inquiry, not disbelief. Disbelief would be clearly the negation of belief. And he would say doubt and inquiry, he doesn't say that in this sentence, but doubt and inquiry are very nice examples for complements of belief rather than the negation of belief. And you can discuss other notions which actually Niels Bohr suggested very often. Justness and goodness, Gerechtigkeit und Güte, he thought would be complementary. Of course, goodness is not being good is not the same as being unjust. So unjust would be the negation of just, but good would be the complement. Truth and clarity, another favorite example of Niels Bohr. Freedom and anxiety, and if you do an exegesis of Bohr's philosophical writings, you can write up at least 100 such examples. The key point here is in this non-Boolean logic, as we call it, the negation differs from the complement. That's the key point. If we would have negations here, then we would get back to the distributive law. But these are complements. That makes the story different. And of course, this also means, it's another important point, that the tertium non datur, the law of the excluded middle, as some say, of Boolean logic, of two-valued logic, does not apply in this logic. So quantum logic non-Boolean logic does not have the tertium non datur. So we can have more truth values than simply true and false, 0 and 1. We can have additional truth values. And why can we have them? Because we have a complement that is not a negation. And of course, this story here, as I said before, this is the wider scope. Here we don't make any measurements. We just make statements. And we can make statements for many systems, not only physical systems or chemical systems. We can make statements also for philosophy of mind investigations and so on and so on. So in this sense, if we, and it's yet it's a formalized, it's a rigorous way to address the question. So that's, in some sense, it's power, notwithstanding the generality of the cases in which it can be applied. So this is, I think, a very important thing here. I have another view graph here, which I probably should also skip. This was intended to give you an additional quantum mechanical topic here, entanglement, but I will not go through this in detail because my time is actually not, it's very finite tonight. And rather than talking about entanglement, I will go back to or come to the last section of this talk, and that's the section about current applications to psychology. And with the first slide in this section, I want to actually repeat something which I said before in words. I want to repeat this very important issue of what a measurement does in classical versus in quantum mechanics, and then I want to make the bridge into psychology on this basis. So observational or measurement processes, I said that before actually, they are interactions of an observing system, let's call it O, with an observed system, let's call it S, and here we again have the state of the system. The system is always in a certain state, and we have these observables, the properties which are associated with the state. Now we can have, these interactions can be of two forms. They can be weak or they can be strong. If they're weak enough, then they're really very weak, then this observing system or this measuring system has no significant effect on the observed system. And that's the situation which I described a minute ago as the situation in which the measurement is only conceived as a registration of a value. Right? There's nothing else because the interaction is so weak. If the interaction is not weak anymore, let's say it's very strong, then of course the observing system or the measuring system has an effect on the observed system. And then of course this makes a difference. And the difference which it makes is the difference between only simply registering a value and registering a value plus changing the state. This is what happens when there's a strong interaction. Now in physics, the case of weak interactions, that's the case of classical physics, more or less. And here we have, according to this no significant effect, we have a commutative behavior of the observables. It doesn't matter whether you measure A first or B first, the result will always be the same for B and for A. Why? Because the state psi is not changed. In the quantum situation, that's what I told you before. We have the non-commutative case where the exchange of the sequence of the measurements really makes a difference. Why? Because the state psi is changed by the measurement. Now in psychology, now this is a claim, but it's a very plausible claim, I would say. In psychology, almost every action of an observation, let's say of a mental system, almost every action entails a significant effect on the observed system. When I ask you a question, you don't know which question I ask you. I ask you a question. then already this asking a question changes your state, because at the moment I ask you the question, you start thinking about the answer, of course. So you're not in the same state. You get into another state. So your state is changed, and of course your answer will be the registration of the result. That's why I'm saying, really, this is the generic case in psychology. And for that reason, non-commutativity will be the rule rather than the exception. Must be the rule rather than the exception. And this claim has led a number of research groups all over the world to really study these non-commutative effects in psychological situations for, let's now say, maybe 15 years or so. And there are quite developed areas of application so far. I'll give you a brief list. One of them, for instance, non-separable concept combinations, semantic association. There is a group in Brussels, Dietrich Arts, and there's an Australian group. Reinhard Blutner is in Amsterdam and also here in Berlin. That's one thing. Then pattern learning and recognition. You can of course study learning processes. Typically, when you study them theoretically, you do that on networks. You have supervised learning or reinforcement learning and all these different kinds. That's something we have done extensively. And in learning, it's actually also clear very intuitively how this non-commutativity comes in. Because if you're a bad learner, I'm talking about networks now, not about people. If the network is a bad learner, then it learns something and can only recognize the learned patterns in the same sequence, right? So it's like when you learn a foreign language, then you learn individual words, like in Germany we say Vokabeln, okay? And then when you learn the Vokabeln, these words in a certain sequence, then some people have a very easy time to repeat them when you're asked, when they are asked in the same sequence, but when they get mixed, they get into problems. So this is non-commutativity, if you want, at its best. The sequence plays a role. Order effects in surveys, questionnaires, something which people know for a long time. When you exchange the order of questions in a survey or in a questionnaire, then you get different answers. Not for every question, of course, but generally you get different answers. And this is known for a long time, but there's no theory. There has been no theory about this for the same long time until, this is not long ago, maybe 2 or 3 years ago, people at the University of Indiana at Bloomington and Hartmann Römer, together with myself, we wrote 2, I think, important papers to how this can be clarified when you really go to a non-commutative theory of questions and answers. Next one, cognitive decision processes. I don't need to go through all these details here. But the next one, the final one, that brings us back to the topic of bistable perception. And I want to tell you a little bit about this model that we have developed here about bistable perception. For 2 reasons. One reason is that it has turned out to be a kind of paradigm, a toy model for studying bistable perception in many different ways. And you see the first publication here was in 2004. That's now almost 8 years ago. And we had, we made a lot of empirical predictions even, and groups in several laboratories worked with these empirical predictions, and essentially everything that we predicted is now confirmed experimentally. But the other reason is that I want to tell you a little bit about this notion here, temporal non-locality, because that is something which arises out of complementary features in bistable perception, but addresses something which philosophers and psychologists have been obsessed with for more than 100 years. I will come to that. Now, this is another kind of ambiguous figure, which you also, all of you have seen before. This is the famous Necker cube, a Swiss geologist, Louis Albert, I think, Necker, detected. He was actually a crystallographer, I think, and so he was drawing kind of pictures on a sheet of paper in order to visualize some configurations of crystals and so on. And then at some point he realized that this figure here, when you look at it for a few seconds, then you see that it switches usually from this one, which is the initial configuration, to that one. There's a bias in the initial configuration for this Necker cube, and the bias prefers this one as the first stimulus that you see, the first representation, and then after a few seconds it switches into this. But of course you have to look at this one here to see this. Am I right that you all know this? Yes. Okay. Now the idea that we had has been to develop a kind of formal model to describe simply the switching behavior between these two representations. And as you will see in a minute, this works extremely well with the notion of complementarity, but now complementarity is not used as a relation between this and that representation. In our model, complementarity is used in a different way, which is hidden behind what you see. So it's an abstract notion. It gives you a kind of dynamical access to the whole story, not simply a kind of a picture of these two different representations. It's an interesting exercise because it shows you in some way that simply considering these two as complementary might be a little bit too naive. Or maybe it's still valid, but if you go behind what you can immediately see in the manifestations here and here, and use the notion of complementarity at a deeper level, then you can learn interesting and more things. So this is we call it the Necker-Zeno model because, as you will see in a minute, some ideas of the ancient Greek philosopher Zeno play a role here too. And what you see here is, you again see these two beasts here. We had them before. So what you know already is that they are non-commutative, right? These two. But here they are used to describe two kinds of processes which play a role in bistable perception. So we really go into the details of what's going on in this switching behavior here. We have one dynamics that's simply the switching dynamics, and this matrix here now tells you whenever you are in this first state, then the probability to stay here is 0, and the probability to go into the other state is 1. And once you're here, then the probability to stay here is 0, and the probability to go back is again 1. This simply gives you a sketch of a kind of switching behavior without timescales still. No timescales, but it's just the structure of a periodic process that is represented here. That's simply the switching dynamics. You go from one perspective to the other one, and then you go back, and The second process here is what we call the actual observation process, and that is, of course, not only the switching dynamics, that is really the projection of the stimulus into one of the two categories, one of the two representations. And what does this matrix tell you? Whenever you are in one representation, then you are there. There's the state probability now. And when you are here, then you are not here. When you are here, then you are not here. And these two states don't occur. So this is another kind of dynamics, which we call the observation dynamics. In technical terms, it would be a projection onto the eigenstates and of the system. And now what we do is we just incorporate these two different kinds of dynamics in a certain mathematical way. I don't bother you with this. I show you what the result is. Of course, this is that I told you already. A and B do not commute. The switching dynamics is an oscillation with period t0. That's now this switching dynamics here. You can introduce some cognitively reasonable timescales here. And the observations happen in successive time steps, separated by this time interval delta t. And these observations simply project onto one of the two states, one of the two representations. And if you do the mathematics of this model, then what you find is something very interesting, and that brings in the Zeno thing. The effect of the observations that take place with these intervals stabilize the system, although it actually is in an unstable state. Okay, this switching is, of course, a kind of process which always destabilizes the state in which the system is in that particular moment and leads you back to the other state. So the system is actually unstable, but the effect of the observations is that the system is stabilized. And the more often you observe, the smaller these intervals delta t are, the longer will be the stable parts in this process. So at the end, if you have delta t equals 0, if you would have this, then you would observe, all the time without any pause, without any interruption. Then the system would be frozen in one of the two representations. There's this saying, a watched pot never boils, right? That's what happens here. And if you there's this one of these, Zeno has published several paradoxes. There's this one Zeno paradox with the flying arrow, and Zeno argues, actually this is a misunderstanding. There is no flying arrow. The arrow is always in rest. Why? Because the arrow, when people say it's flying, it's at any time. It is at one particular well-defined point in space at any time. So it's always in rest. Then this means it must be in rest. The flight is an illusion. I mean, Zeno was in this Parmenidean school of. We can talk about this later. So this is the relation to the Zeno, which figures in the name that we gave the model. So anyway, this very simple equation. That's the one which leads to a huge number of empirical predictions that you can or many of them you can test. You can go into the laboratory and test this. You can, for instance, check whether the timescales really have this relation. You can try to manipulate one of these timescales as an independent parameter. Then you can measure the dwell times, switch the times during which the system stays in the same representation state, and then you have this and you have this, and then you can try to find out the size of delta t, and you can make a lot of experiments. And as I said before, there's a lot of confirmation for this model. So we have over the years, we really developed some kind of trust that this model cannot be too wrong. And now I come to the last part of this presentation, which I hope will generate a little bit of interest in you. And this is a conference. This is a consequence of what comes now is really a conference of the complementarity of these two kinds of dynamics. This has the title of temporal non-locality. What do I mean by this? There's a long-standing question in study of time and study of perception, and this question can be phrased this way. Can mental events or mental states of subjects, experienced states of subjects, always be uniquely assigned to instances? And by instance, I mean just a point in time without temporal extension. So it's just when it begins, this instance, then it's already over because it has no extension. And the question is that really a proper way to describe mental states and subjective mental experiences? We know that there have been some prominent figures in the history of philosophy and psychology. I mention only three here: Henri Bergson, William James, we saw already, and Alfred Whitehead, and they all three of them, and there are many others, answered this question to the negative. And they did that with different notions. Bergson had this notion of durée, in English translated as duration, something like that. Or William James had the specious present. Whitehead had the notion of an actual occasion. And all these entities express that in philosophy there has always been a kind of trend to consider mental events or mental states as states which have temporal extension. So they are extended in time. There are states which are not punctual between past and future. They are just that. Husserl should also be mentioned here, of course. I forgot to write them. But they have extension, and that means the present for an experiencing subject has extension. The present is not simply a point, it's an extended thing in time. So these temporally extended events are, in all these philosophical approaches, are conceived as sort of intervals within which no further temporal segmentation or something like that is possible. So within this length, let's say, I just say a number, 30 milliseconds, for instance. Within these 30 milliseconds, you are not able to assign relations like before or later, because it's a kind of unit which cannot further separate it into parts. It's a kind of temporal whole, if you want. And this gives rise to the notion of temporal non-locality. Now, in quantum theory, this kind of non-locality, not in the same way as here, but structurally in the same way, is a rigorous consequence of complementary or non-commutative operations. And that brought us to the question, or to the idea to study whether the model, this Necker-Zeno model that we developed, whether it indeed predicts something like this temporal non-locality, because we have two kinds of complementary or non-commuting dynamics. And really, when you do the calculations, and I cannot go through that in detail, of course, then you see that the model predicts violations of temporal locality. So what the model actually predicts is that these ideas by Bergson, James, Whitehead, Husserl, and others are really realistic as far as the experience of the present, the subjectively experienced temporal present, is concerned. Again, it would of course be interesting to do experimental tests which show that the prediction of the model really can be found empirically, but we are not that far yet. Let me finish this talk with, I think, with a nice quotation by someone who has been interested. Sudarshan is a physicist, a theoretical physicist. He has been interested in these questions of how time is perceived for a long time himself. And if you look deeply in his eyes, you will see that he is actually a monk. He's an Indian physicist working in Austin, Texas, but he's actually a monk. So he suggests a mode of awareness in which, and this is again a quotation here, in which sensations, feelings, and insights are not neatly categorized into chains of thoughts, nor is there a step-by-step development of a logical legal argument to conclusion. Instead, patterns appear, interweave, coexist, and sequencing is made inoperative. Conclusion, premises, feelings, and insights coexist in a manner defying temporal order. That's his description of this temporally non-local extended present. In this present, you, as he says, there is no temporal order itself, only outside it. We have temporal order as we usually experience it. So this is of course, this is something which you can, therefore I mention it here, you can relate this to bistable perception. And I think it's a very fascinating topic, which really is now very interdisciplinary and very broad because it contains elements of mathematical physics, it contains elements of perception psychology, it contains elements of the philosophy of time, and at the same time, it's a kind of picture which is sharp enough or specific enough that it really allows you to do research on it. So it's also a very nice, I think, a very nice domain in which you can, given these very broad notions, you can make very detailed research in philosophy and psychology, and of course using elements of mathematics and physics. Okay, so that was it for today. You will realize that I have not talked, when I talked about bistable perception, I did not talk about non-Boolean propositions. I talked about non-commutative observables here. Of course, in some sense, a formulation in terms of non-Boolean propositions would be an equivalent way to describe the situation, but of course then you cannot go into the lab and measure anything. So that's the reason why I did it this way. The disadvantage, as I mentioned before, when you have the algebraic picture, is that you have the narrow scope. You're really interested in let's say, purely philosophical questions, then I would say it's a much better choice to go to the propositional logic picture, to the logical picture, and apply this. And there is still a lot, I can tell you, there's a lot to get when you go this direction. It's totally unexplored territory. With very small steps, you can come very far. Thank you very much.
Well, thank you very much for this really fascinating talk. And I can see there's one, perhaps, yes? Or am I right?
I saw one, yes.
Yes, okay. So I'll hand it over.
So I just want to ask a question about quantum logic and the status. I mean, am I right in interpreting what you're arguing as sort of within the strong tradition of quantum logic that one finds in, say, like the early Hilary Putnam essays, in which one's not just claiming that a non-Boolean logic forms a suitable model for some way of representing the observables, but these things really are propositions. Thus, what's true in all models of the non-Boolean logic gives the correct logical truths for the world. These and so like classical laws like distributive law, like the inference from the left to the right side of the distributive right conditional are not truth preserving. Mm-hmm. I take it that you're committed to that strong thesis. So I'm just curious how you would respond to these two sort of very well-known objections to that view that you can find like in Quine and other things. One is that quantum logic is really just changing the topic, that you don't mean, that I mean, you would only think that that's a violation of distributive law if you interpret the connectives as meaning meet and join on a non-Boolean logic. And so the classical logician is just going to say, well, that's just not what the classical connectives mean. And the second objection is that quantum mechanics, of course, is developed in classical mathematics, formally, if you want to go in like in ZFC or something, and that is done against a background of classical logic. So there's a worry that in arguing for like really strong revisions of classical logic on the basis of quantum mechanics, that one is, as it were, cutting off the branch one is standing on. So I'm just curious how you would respond to those objections.
Of course, this was, in some sense, this was the very quick picture, right? I just wanted to, in this talk, I wanted to give a sense what, actually you can go farther back still than to Putnam, because the first papers were von Neumann and Birkhoff, and that's already in there, essentially. The more modern picture is not that you simply insist on a non-Boolean logic. The modern picture is that what people now call partial Boolean logic. And that brings us to the work, I mean, you obviously have studied that quite well, to the work of Ernst Specker and Simon Kochner, these people. And there you have, in a partial Boolean logic, what you have is you have sublattices, which are Boolean, but they are in some sense pasted together in a non-Boolean way. So in that is a much richer picture, of course. For instance, the Cauchy-Specker theorem precisely makes use of this kind of logical formulation, which does not, let me say, drive the pure non-Booleanness too far. It still keeps, and it's in some sense it's in agreement with what Niels Bohr always said. Niels Bohr said, whenever you make a measurement, no matter whether you make a quantum measurement or a classical measurement, your measurement apparatus has to be classical. So what you measure has to be 0 or 1, right? And in that sense, the partial Boolean logic really combines the Boolean picture that you still need with the non-Boolean picture. And point 2, I would say, of course, this is a very difficult thing in logic, and also, I mean, when you go into non-commutative observables, for instance, there are so many complications when you go into the details that you can fill up seminars simply with the complication that you get when you look at position and momentum as observables, because they have a continuous spectrum, they are not discrete, and all this kind of stuff. I omitted all these complications, including what you said about the objections to Putnam and so on.
Thank you very much. I really enjoyed it. I'm not a scientist, at least I haven't been a scientist for many years. I come from a completely different humanities background, and I was struck by the way that some of the relations that you're talking about reminded me of rhetorical terms like hendiadys and oxymoron, but that's something that I'm going to follow up. The question that I've got is going back to what you were talking about when you were talking about the way that in psychology, virtually everything is a non-commutativity. And I think I get it right that you said that almost every action of O entails a significant effect on S. Now, is it the case that you would always put it that way, that O is having an effect on S? Cannot the presence of O make S respond does it matter if it's S responding or O having the effect?
First of all, I wouldn't insist that it's always the case. I would say it's the general case. Okay. And again, we can have specific situations in which this is ignorable or something. Yeah. But really my claim is it's the general case. And so maybe I can illustrate once more why I think this. Would that be okay with you? Yeah. I
perfectly accept that it does. It probably does occur in many cases.
Yeah.
I'm just wondering if it makes a difference if it works the other way around.
If it does not apply, yeah, I'm saying it's the rule. It's the rule rather than the exception. Now,
I'm not actually asking that. What I'm asking is, does it? How do you know when S changes because of O? How do you know that it's because O has had an effect on S, rather than that S has chosen to change because of the presence of O?
Has chosen to change. Yeah, okay. So the situation is about, the situation that I have in mind is really a measurement-like situation where you make an observation which is intended to learn something about a system. In this case, it's a mental system, something. Of course, there are also interactions without any intention. We always interact with the environment, and then the situation is different. But maybe this is the simple-minded background picture of a scientist that when you want to interact with someone, that it is for an intention, then it's a kind of controlled interaction that you want to do. And then I would say my picture applies. But if everything is, say, free-floating, then Of course, this can happen. Also, if you look at, maybe this is an interesting one. If you look at the person who asks the question, of course, this person also brings himself into a certain state, which enables him to ask the question. And this is, of course, something which he wants to do himself. This is precisely what you're saying, right? Yes. But then he asks the question, and then the simple-minded scientist picture is he makes something like an experiment. He makes a measurement on another subject's mental state, and that subject's mental state is, of course, influenced by that question, if this subject takes the experiment seriously.
Yeah, that really is my question.
Yes. Of course, you can. When I ask you something, you can say, this guy can ask me many questions. I'm not so stupid to react to that, of course. That's right. Then it's much more complicated. And I would say even the measurement problem in physics is still, after 90 years, not completely solved in quantum mechanics. So there are some people who say when we want to formalize measurement, then we need a theory which exactly takes into account what you're saying. Not only when you do controlled measurements, but in a more general sense, every interaction that a system has with some other system must in some case share these features of measurement, because it's in a general sense simply an interaction. Okay, now I think we got it. Yeah. Decoherence approaches like Wojtek-Zurex, for instance. Yes.
Can you give an example? Can you give an example how actually this measurement process changes the observable? I mean, physically speaking?
The state. This is hard to do because it's a difficult thing, because immediately when you talk about things, at some point you slide into classical thinking. But if you allow me to do that, then of course I could say, this is an old example which has been discussed in the 1920s. If you want to measure the location of, say, an electron, what you do is, for instance, you do diffraction experiments or whatever, you radiate at it, right? But now if you are in the particle picture, then of course your radiation is also consisting of particles. They have momentum, right? So, and then you measure, of course you can measure the location of your electron with these particles, with these radiation particles, but at the same time, the radiation hits onto the particle and moves it somewhere else. So the location is in some sense registered, but at the same moment it's changed. And it's not the same after the experiment. But this is classical thinking. It's a kind of it's an attempt to explain the situation in classical words. What is a spin, for instance? People, when you interpret the spin classically, then some people say this is a kind of angular momentum of a particle rotating around itself. This is, of course, complete nonsense. There is no such particle in quantum mechanics. A particle is really a classical simplification of something which is much more complicated and much more abstract. Some people like Eugene Wigner, who you may have seen when you were in Princeton. Wigner had the mathematically purest description of an electron, and that is simply an electron is a representation of the non-homogeneous Lorentz group. Period. It's very abstract, but probably very true also. So I'm saying this as a caveat. My example was very hand-waving. So.
Can you explain it in non-classical terms also?
This is the point where you have to bring in the blackboard.
If you can explain it in non-classical terms as well.
Yeah, it's not easy. Will you be here tomorrow?
Not sure.
Not sure.
can, yes.
I think that explodes the framework of this thing here. I mean, what one can say abstractly is that the interaction of the observing or measuring system with the measured system really, I mean, there's this notion of the state, right? So it's not simply that something which we don't know really is changed, the state is changed. And that has to do with the usual representation of the state in Hilbert space. It also has to do with the essentially it goes back to the non-commutativity, right? The states for non-commutative systems, the states are always dispersive. So the states have they are not sharp. So in a state space, you cannot represent them point-wise. They're always, somehow blurred or something, right? And a particular feature of quantum mechanics is that whenever you make a measurement, you never know, and you don't have under control which part of this blurred distribution you actually get access to. You just take something up. That's what people call ontological randomness in quantum mechanics, right? You take something out that you measure, and this something that you take out, of course, has an effect on the rest of the distribution, and that's what amounts to the state change. Maybe that's a good way to put it. Also makes clear why this doesn't happen in classical physics, because in classical physics, the state is always a point. And then you can simply register. Take your value out, nothing changes, because it's not a distribution.
Thank you.
Everything else clear. Good.
Maybe I have a question.
Yes.
I wanted to ask you, for example, the two examples that we also stressed very often, that is one, the sort of Necker cube, and the other one, the Rubin vase.
Yes.
But I was always thinking that, for example, anamorphosis, like the famous Holbein picture where you have the skull that sort of turns into sort of non-easily recognizable object, that there, for example, you have also a different instant, like what you mentioned with the durée, or at least I always experienced it that way, that you somehow have a sort of extended perception.
My suspicion is that the durée state, I mean the temporary non-local state, is precisely that mental state in which you are when you are in between the representations. So you're kicked out of the one, you know what I mean, and so you're out of the first one and not yet in the second one. Then you are in the state in between, and of course since that state is unstable, it happens to be very short in time. But then we can ask, for instance, is it possible to extend that state by certain techniques, for instance? Therefore, I stress this guy as a monk because he knows a lot about meditation also. And he would say it's very easy for me to really stay in that in-between state for a time which is long enough to experience it and introspectively try to find out what its qualities are, right? That would be the non-local state. Now, and I think, there's the Necker cube is a very simple thing. And when you do science, in this case psychophysics, with ambiguous figures, then you are interested in figures which are as simple as possible. And this means figures which have almost no additional semantics except this three-dimensional representation. And the Rubin vase is also a very simple thing. When you add semantics like the old and the young woman or the duck and the rabbit and all these other, and then you can come really into, if you look at paintings of Dali, for instance, you sometimes have ambiguities, 6 or 7 or 8 ambiguities in one picture, right? And then it gets, for scientific purposes, I would say you're dead, because you cannot say anything with those. But when you look at the whole thing in terms of life world, lebensweltliche, life world connections and stuff. Then, of course, the semantically poor pictures are uninteresting. Then you want to know about the others. So there's, again, some kind of tension. But then it becomes very difficult to do science with them.
Just ask about, I mean, maybe about this question about the precisely the very simple Necker-Zeno example, because you have 3 time variables, no? I mean,
Yes.
And are they all, I mean, could you say just a little more how you control them? Because it seems like the only thing you can measure is one or the other. I mean, how do you have access to it?
What can always be measured is the average of t, because that's what we call the dwell time. That's the time which it takes the subject to get from one representation into the other one, right? So when I have perspective 1, then it typically takes 2 or 3 or 4 seconds, and then it switches. So that's this t in brackets. The t0, that's an artificial time scale. It has to do with it's sort of the time scale for the Hamiltonian of the system. I only say that to him because I know. So this is the time scale with which the system would switch where there are no observation operator, right? And the observation comes in and changes this t0 to t in brackets. And why does it do so? Because there's this delta t, that's the kind of, you can consider this as a kind of update interval where information becomes measured. And that's the time scale which we know from experiments would be something like in the order of 30 milliseconds. Ernst Püppel, this goes back to experiments by Ernst Püppel in Munich. So now, first of all, we can say that the time scales that we know that correspond to these 3 different these 3 different terms here, they are, in cognitive science, there are 3 time scales which are discussed precisely in that way. And those are the 3 second, the 300 millisecond, and the 30 millisecond. So this would already satisfy this equation, right? Because the t0 is the geometric mean of the other two time scales. Now, what you can do is you can, with an experimental trick, you can manipulate the t0. What's the trick? The trick is that you do not present the Necker cube simply continuously. You switch it on and then it stays. You switch it discontinuously. You present it discontinuously. So you present it for a second, then you take it away, blank screen, for instance. Wait for, 600 milliseconds, then present it again, and so on. And now by the interstimulus intervals, the off times with a blank screen, you can extend, when they are longer than 300 milliseconds, then you can extend this t0 like in a kind of effective Hamiltonian model. So when you do the discontinuous presentation, you can, at least for values larger than 300 milliseconds for the interstimulus interval, you can extend your t0 in a very controlled way. And then you plot your t0s on the x-axis, plot, for instance, your t's, the measured dwell times, on the y-axis, and then the model predicts that you get a quadratic curve, first of all, and the curvature should be the delta t, independently measured now. And that's what happens. And then there are additional complications when you go to values, interstimulus intervals below 300 milliseconds, because then you cannot modulate the Hamiltonian anymore, because the Hamiltonian would already be the 300 milliseconds. And then we get another kind of behavior which the model predicts, which is just the other way. It doesn't increase toward longer t0s quadratically, but it increases toward smaller values. And this is kind of counterintuitive in some sense, but it's predicted by the model again. So, and things of this type. Also, the distribution of the dwell times is a non-trivial thing, right? It's not it's not Gaussian, of course, because it's limited on the lower end by 0. So it's a kind of what people call a gamma distribution. It's a distribution which increases polynomially and then decreases exponentially. And then you can fit the parameters, and from the parameters you can again extract information about the timescales. And there's 8 years is a lot of time. Right? You can test a lot of things. I can send you some publications about that with the details. Okay.
Right, so if there are no pressing questions right now, I think we can stop here right now and then go upstairs and continue our discussion.
Thank you very much.